Okay, let's get started. First, something about the final time slot. I said that there shouldn't be too many overlap issues. That's actually because I deliberately scheduled enough overlap on both sides. Officially, our exam time slot is only 4 hours, but I scheduled an extra hour before and an extra hour after, so that, if you have another exam right before, well, you've got that extra hour after, so that you don't have to immediately go from one exam to the other. And likewise, if you have one immediately after. I might expand the time slot a bit beyond 4 hours. I'll let you know whatever I finally decide, but whatever I do, if I give you more than an hour before the official 9 through 11 time slot, I'll give you more than an hour after the official 9 through 11 time slot. Anyway, last time we were talking about Legendre polynomials, which satisfy the equation 1 minus x squared times the second derivative minus 2x times the first derivative equals minus L times L plus 1 times PL. And if x equals cosine theta, then they also satisfy 1 over sine theta times partial by partial theta of sine theta partial PL partial theta equals minus L times L plus 1 PL. And so if we just divide both sides by r squared, then in that Laplacian operator, which is 1 over r partial by partial r, this should be r squared. If psi is the name we're giving to our solution to the wave equation, then this whole mess, this part of it, if psi is proportional to PL of cosine theta. So the way to think of it is we've got the Laplacian operator. It's a mess. You use it on some function of r, theta, and phi. There's a bunch of messy things going on with theta. But all of that turns into this. It turns into something much simpler if psi is proportional to PL. So if you've got something proportional to PL, you can just replace that mess with minus L times L plus 1 times psi over r squared. That's what we established last time. And we established that these solutions are well behaved, meaning that they converge for all values of theta. It's not like there will be some values of theta where they blow up. Now, any questions on that? Anything at all? Okay, Legendre polynomials have many, many, many properties, and the book has quite an elaborate run through of those properties. I'm not going to say that they're useless because I've used some of them. I've had projects where I've had to do very gory things with Legendre polynomials, but I've only used a fraction of those. And someone else has used a different fraction of those. So rather than trying to go through all of those, I'm going to go through a few properties that are similar to properties of other solutions to similar equations because they illustrate ideas that show up a lot. And if you can learn these, then if you should ever have a project that requires you to learn gory details of Legendre polynomials, you can learn whatever other properties you need. Or if you have to, instead of Legendre polynomials, you have to learn Hermite polynomials or confluent hypergeometric functions or Chebyshev polynomials or whatever, you can do those. So let's start with a very important property, orthogonality. We showed a couple months ago when we introduced these just by fiat that the integral from -1 to 1 of PL of x, PK of x, dx was equal to 0 unless L equals K. I'm going to prove that now. I'm going to prove that by starting from the fact that we could rewrite the Legendre equation as d by dx of 1 minus x squared dPL dx equals minus L times L plus 1 PL, which means that PL would just be all those derivatives divided by minus L times L plus 1. So I could rewrite all of that as minus 1 over L times L plus 1 times all those derivatives. So then the integral of PLPK dx would be the integral of, well, let me put the 1 over L, minus 1 over L times L plus 1 out front. There should be PL there. And then we could use integration by parts. U is PK, dV is all of this, which means du is equal to dPK dx times dx. And V is 1 minus x squared times dPL dx. When we do integration by parts, we're going to get UV minus plus, because we got the minus sign up front, integral of V du. So we're going to get minus 1 over L times L plus 1 of 1 minus x squared PK dPL dx, evaluated from minus 1 to 1, plus 1 over those L's Any questions on how I got here before we start interpreting it? Well, let's look at this thing evaluated at minus 1 and 1. I don't know what PK is going to be at minus 1 and 1, and I don't know what the derivative of PL will be at minus 1 and 1, but I know that 1 minus x squared is going to be 0 at both ends. So that means this whole thing is 0. Well, that's nice. So what I'm left with is I'm left with the integral of PLPK just being equal to all of this. This is, in linear algebra terms, the inner product of those two functions. Now, okay, well, how does that, it's not immediately obvious to the eye that this must be 0. I mean, somebody could say something about the endpoints, but so what? It's non-zero. It's non-zero, and in fact, at least this thing is positive everywhere between the endpoints. So that doesn't mean much. But what if I switched it around? What if instead of writing PL in terms of this derivative, I had written PK? What if I said PK is minus 1 over K times K plus 1 d by dx 1 minus x squared dpk dx. There's no rule against that. There's no law against it. I'm not going to be fired for deciding to swap P and to swap L and K. All right, the American Physical Society won't revoke my membership for that. I could have written PK in those terms. So I could have done it the other way and had PL times all of these derivatives. And if I had PL times all of those derivatives, then I would do integration by parts again. And in the end, I would get the exact same expression because everything here is the same if we swap L and K. You know, I have those two arrows to mean that we replace one with the other. So we switch them around. If L got replaced by K and K got replaced by L, I would get the exact same integrand. I just have a different prefactor up front, which means that 1 over L times L plus 1 times the integral of all that mess is equal to 1 over K times K plus 1 times the integral of all that mess. So let's look at that. I've got same integral multiplied by two different things. Thoughts on that? Questions on that? What's the implication of this? Someone.
The inner product is non-zero.
It's non-zero?
Correct. It's 0.
Well, but why? Fine. I mean, okay, I've given away by tone of voice that it's 0. Now the interesting question is, why is it 0? Other than the fact that my tone of voice says it's 0. But what's the
because they're
to that?
They're orthogonal to one another.
Well, we're proving that we're orthogonal. You're assuming the result.
I'm out of answers.
Someone else.
In order for that equation to be satisfied, L and K have to be the same.
Say that a little bit louder.
In order for that equation to be satisfied, L and K have to be the same, which is the only way that that integral is positive, or like non-zero.
Non-zero, yeah. Because if I call this integral I, then what I've got is that I over L times L plus 1 equals I over K times K plus 1, which is nonsense unless I equals 0. So that inner product must be 0, all right? And this means that Legendre polynomials with different indices are orthogonal. This is a lot like the fact that for Hermitian matrices, eigenvectors with different eigenvalues are orthogonal. And in the last week of the semester, we'll pursue that idea a little bit further. And I'll try to make at least a few of the connections there in the time that we have. But just like eigenvectors with different eigenvalues have to be orthogonal, functions with different eigenvalues have to be orthogonal. And the proof is a lot the same. If you think back a month or so, when we proved that eigenvectors were orthogonal, we took some inner products. We take, like if we had a Hermitian matrix, we take V1 times HV2, and we would show that that has to be equal to V1 sorry, HV1, V2, and then we would show that that is 0 unless lambda 1 equals lambda 2. That was the only way for those to be non-zero. And here we're kind of doing the same thing. We're computing this inner product two different ways, and we're getting two different answers, which is impossible unless those two answers, or we're getting the same thing multiplied by two different numbers, which is impossible unless those two numbers are 0. Any questions? Now, for reasons of history, people decided not to make the inner product of PL with itself equal to 1. That would have made far too much sense. So instead, the way that people usually write these things down is that PL of x squared is equal, the integral of PL of x squared is equal to, let me make sure I get this right, 2 over 2L plus 1. Why? Why is it that way? Well, somebody decided that they want PL of 1 to equal 1. And then if you follow a long chain of twisted logic that I'm not going to try to replicate, you wind up getting this relationship. Not my idea, but that's what someone did. We don't tend to use them in that form a lot, but I'm telling you about this so that you're not surprised when you look in a book and you see these weird things where the inner product of PL with itself is not 1. I don't want you coming to me and saying that I must have said something wrong because you thought that all of these things are form orthonormal bases, where normal means that its norm or its length, its inner product with itself is 1. For historical reasons, when people first wrote down these Legendre polynomials, they weren't yet committed to the idea of having things form orthonormal bases, so someone normalized them this way. This is just a curiosity. We will be using them in a somewhat different form that I'll get to either the end of today or we'll cover it briefly on Friday before you do an activity with it. We could also derive the Legendre polynomials from orthogonality. Suppose I just said that P0 of x is 1 and P1 of x is x. Then require P2, P4, P6, etc. to be even. So P2 is just A plus BX squared. There's no linear term in there. And require P3, P5, P7, etc. to be odd. So P3 is equal to C plus CX, plus DX cubed, all right? And finally, require all PLs to be orthogonal to each other. Well, the even and odd ones are automatically orthogonal, because if I've got the integral of PL, PK, dx over an interval that goes from -1 to +1, if L is even, and K is odd, the product is odd. And vice versa. If L is odd and K is even, again, the product is odd. And the integral of an odd function from -1 to 1 is 0. So let's figure out the integral from -1 to 1 of P0, P2 dx. So that's going to be the integral from -1 to +1 of 1 times a plus bx squared dx. Well, let's see, the integral of a is just x, sorry, ax, my bad. And the integral of bx squared is bx cubed over 3, evaluated from -1 to 1. So that's going to be 2a plus 2b, 2a plus 2b over 3. I'm searching for a Hamlet joke and it's not coming. And that's got to be 0. So if a equals 1, which we can always assume because remember, these things are solutions to a linear differential equation. I can set it equal to 1, and if somebody says, no, I don't want a to be 1, I want a to be 53.6, well, then we just multiply the whole thing by 53.6. All right, so a is 1. So I've got 2 times a plus b over 3 equals 0. So that means that b must be minus 3a equals minus 3. And P2 of x then is 1 minus 3 x squared. And if you check a table, if you look in the textbook or you look on Wikipedia, which actually has a perfectly good table of Legendre polynomials, then you will indeed find that P2 is equal to this multiplied by some constant. And likewise P3, all right? So we've got Cx plus dx cubed. And we already know that P3 is proportional to P0 and P2. And now we need to be, sorry, it's orthogonal to those, my bad. Now we need it to be orthogonal to P1. So the integral of P1, P3 dx will be equal to the integral of x times cx plus dx cubed, whole thing multiplied by dx, which could not possibly cause any confusion here. So we've got the integral of cx squared plus dx to the 4th dx, which is cx cubed over 3 plus dx to the 5th over 5, valued from -1 to 1. And that is 2c over 3 plus 2d over 5. Again, we can factor out the 2, and we can set c equal to 1. And we get that d is equal to minus 5/3. And you can look at a table of Legendre polynomials and you should find something that looks like that, except maybe multiplied by some factor. Any questions? It's a nice property of the Legendre polynomials that we can construct them purely by requiring orthogonality. Now you could say, what about P4? Now I'm not going to do it, but P4 would have 3 coefficients in it. The coefficients of x to the 0, x squared, x to the 4th, and we have 2 orthogonality requirements. It's got to be perpendicular to P0 and P2. And then we've got 3 unknowns, 2 equations, 1 arbitrary coefficient, because again, you could always set one of the coefficients equal to 1. And if somebody says, no, I want that coefficient to be equal to 13 because it's my lucky number, then you just multiply the whole thing by 13. And it still satisfies the differential equation. Any questions? Anyone? Going once, going twice? Well, I've been saying for a while that one nice thing about these sets of orthogonal or at least linearly independent functions is that we can write other functions in terms of them. So what if f of x, we want to write f of x as a sum from L equals 0 to infinity of CL PL of x. And we want to do that because we know that solutions to the wave equation can be broken down in terms of Legendre polynomials. So, of course, a real solution to the wave equation is also going to have functions of r and phi, but, you know, baby steps here. Baby steps here. Rome wasn't burned in a day. It took a while to break the whole thing down. So we want to figure out how to compute CL. CL are unknown coefficients. We need to find those. So with Fourier series, let's talk about Fourier series. How did we break down a function into sines and cosines? How did we calculate those coefficients in the Fourier series? Anyone other than Sebastian, because he's asked a lot of questions that I do want to hear from other people. No offense, Sebastian, but I want to hear from other people. Anyone? Anyone? Bueller? Inner product in the chat. Okay, good. So let's take the inner product of f of x and PL of x. Well, that's going to be the integral from -1 to 1, f of x, PL of x, dx. But of course, f of x, it could either be some very explicitly written function like e to the minus x squared, or we could always write it in this form. So we could also write that as the sum from L equals 0 to infinity of CL integral of P, oh, and I should probably call this PL prime. PL of x, PL prime of x dx. Now that's an infinite number of integrals. Okay, we've got a sum of an infinite number of terms. Each term is an integral. But what can we say about most of those integrals in that infinite series? Anyone? Anyone? Bueller? Bueller?
Most of them will go to 0.
Most of them will be 0. It's going to be 0 unless L equals L prime. So we start off with something infinite, and then we do this integral that turns all but one of those infinite number of terms into 0. And so we are left with just CL prime, integral from -1 to 1, PL prime squared of x dx, or CL prime times 2 over 2 L prime plus 1 equals the integral so CL prime is equal to 2L prime plus 1 over 2, -1 to 1, f of x, PL of x, dx. Any questions on how I did that? We saw a result like this with Fourier series. The Fourier series, we found that an was equal to 2 over the period integral from t naught to t naught plus the period f of t cosine 2 pi over t times n times the time dt. And bn was 2 over the period, something similar. All right. You could do things like this for other types of functions. We'll do something like that next week for Bessel functions. In quantum mechanics, you could do things like that with Hermite polynomials or associated Legendre functions. Hermite polynomials show up in the energy levels of the harmonic oscillator, and associated Legendre polynomials show up in the energy levels of the hydrogen atom. In each case, you want to take some function that might be quite messy and turn it into a sum of pieces of simpler functions. And so you just do integrals like this that wind up looking like these inner products, right? The details can be different, you know, a 2L prime over 2 instead of a 2 over the period. In some of these, you wind up multiplying by some third function, but the basic structure is always the same for these kinds of problems. And it's really no different from saying that Vx is equal to V dotted with X hat, to go back to vectors much earlier in the semester. It's just that this is a statement in 3D space, 3D Euclidean space, you know, the space that we're completely used to from ordinary geometry. And this is a statement in an infinite dimensional space. Any questions? And that space is also very similar to Euclidean space, except that it's infinite dimensional. Well, here's one complication. When we're solving the wave equation, usually the thing that we call x in three-dimensional space is a coordinate. So here I've been using x as just a name for whatever the variable depends on, or whatever the function depends on, whatever variable we're feeding into that function. But usually we want to find this as a function of angle. We've been saying that x is equal to cosine of theta. So dx would be minus sine theta d theta. And the integral from -1 from cosine theta equals -1 to cosine theta equals +1 of f of theta is what it usually is, times PL of cosine theta times minus sine theta d theta. Well, let's think about here. What's the value of the angle when the cosine is -1? Euler, anyone?
Pi or 180?
It's pi. And the cosine is 1 when theta equals 0. And then we can just flip those because we got a minus sign up front. And when you multiply by a minus sign, you could also get rid of the minus sign and swap the limits of integration. And that is how you would take a function of theta and break it into Legendre polynomials. You would just take that function and you multiply it by whichever Legendre polynomial you're trying to find the coefficient for right now. You multiply by sine, and you'd integrate. And then you would multiply by this thing here. And so you would get that CL is equal to 2L plus 1 over 2, integral from theta equals 0 to pi, f of theta, PL, cosine theta, sine theta, d theta. Any questions on that? No questions? Anyone? Anyone? Bueller? So I keep making that joke. That's a reference to Ben Stein's character in Ferris Bueller's Day Off, who was playing this history teacher that would drone on and say, questions? Anyone? Anyone? And when he was taking attendance, he kept saying, Bueller, Bueller. And I actually met Ben Stein. I actually won $850 of Ben Stein's money. Back in the late 90s, early 2000s, Ben Stein had a game show on Comedy Central. And I went on Ben Stein's money and won $850. And here's something that will make you guys feel better. I missed the math question. Two angles that add up to 180 degrees are said to be what? And I knew it was either complementary or supplementary, but I couldn't remember which. And it's not like we actually use that name for it. You know, we just say, hey, they add to 180, or, you know, they form a straight line when you add them up, or something like that. You know, we don't normally say, oh, they're supplementary. I think it's supplementary. So I had to guess one of those, and I guessed wrong. If I had gotten it right, I would have gotten an extra $1,000 because I would have tied him. And then I would have gotten $1,850 instead of $850. And anyway, if someone wants to go exploring old torrent sites, maybe you'll find that episode. I used to have a copy of it on tape, but after several moves between houses and whatnot, I lost that tape, or else I would give it to the physics club so you can make fun of me watching it. All right. You got a dead audience today. Nothing seems to be livening you up.
That's really funny, actually. I like
it. Okay. All right.
I'll add one thing to the discussion that I think is pretty cool about this process.
Yeah.
Is that what we're doing, I'm sure you know this, Dr. Small, but I don't think the others do, is that what we're doing when we take the inner product like this, equations, is we're essentially finding the projection of the original function onto the Legendre, I can't pronounce it, Legendre polynomial functions.
Yeah, it's just like taking a dot product of vectors. It's also, for those of you who want to think about it a different way, this is almost the mathematical equivalent of a highly targeted enzyme. You know, an enzyme is used to take things apart in chemistry. And this is a highly targeted enzyme that will take apart, if we think of this function as a whole bunch of things added together, a chain of things bonded together, this is an enzyme that will come in at a specific point on that chain of functions and do two little snips, take off all the things before it and all the things after it. And what you're left with is just this one piece. So this is an analogy I would use with my biochemist friends. This is really an enzyme that pulls something off. And I make these chemistry analogies partly because, hey, it's science, and partly because it helps explain things like, why is it that the pieces of a function can have very different properties than the entire function? And my best analogy for that is that oxygen burns things. Hydrogen is an explosive fuel, but water puts out fires, right? And so likewise, you can add up a few mathematical functions, each of which have very weird properties, and yet their sum might have very different properties than any of the pieces. All right, let me show you two other expansions. One I'm not going to dwell on, but you're going to see this in E&M. So we are at a point in space R. And there's another point in space where maybe we've put a charged particle, R prime. So here's our origin. Here's our observer, person who's got a meter and is measuring a field. And here is R prime, the position of some charge. And this is R minus R prime. If you're not convinced of that, then just take the sum of R prime plus this. And when you add them as vectors, you go from here to R prime to R. The sum of these two steps gives you R. And one of those steps is R prime. So the other one must be the difference between R and R prime. You have to use that if you're calculating potential. And that is the sum from L equals 0 to infinity of the absolute value of R prime over the length of R, whole thing to the power L, PL of cosine theta, and then there's an extra power of R in the denominator there. I don't expect you to memorize this. I don't expect you to derive it. I'm not going to put it on the homework, but it's an example of where these things show up in electrostatics. It's a way of taking something complicated and again, breaking it into pieces. Or let's solve Laplace's equation, simpler than the wave equation. Laplace's equation. Del squared V equals 0. And let's say that we're dealing with the case where the derivative of V with respect to phi is 0. So it's symmetric about the z-axis. Okay, you've arranged, you can have a whole bunch of different charges, but you've arranged them along the z-axis. And that would be a perfectly valid scenario if you just have a linear molecule, whether it's a diatomic molecule or a triatomic molecule, and there are linear triatomic molecules like carbon dioxide. So you've got some linear molecule or some linear set of charges. So everything's going to be symmetric about the z-axis. Then I could write V as the sum from L equals 0 to infinity of some function VL of R, PL of cosine theta. Because we already know that we've got to be able to write as a sum of things that involve PL of cosine theta, right? Because if we write this Laplacian operator in spherical coordinates, then the Legendre polynomials are eigenfunctions of that. And whatever we're multiplying them by has to have all of the dependence on R. And you could say, shouldn't there be a coefficient? And I say, yeah, I'll just fold that into the dependence on R. You know, I'll just say that it could be some function of R, or maybe it's 7.3 times that function of R, whatever. So del squared V is going to be 1 over R squared, partial by partial R, R squared partial V partial R, plus my angular derivatives, which are a mess, over R squared, plus I should have my phi derivatives. These are my theta derivatives. But I'm crossing them out because of this assumption. if I make that assumption, then I could replace this with the sum of 1 over r squared, partial by partial r squared partial VL partial r, minus L times L plus 1 VL of r over r squared. Questions on how I got there?
Yeah, how? How did you get there? How'd you replace that with the sum?
Well, I take my sum and I take the derivatives of it, and I have to take the radial derivative of each term. That's this. And then I take my theta derivatives. Remember, I said earlier today that with those theta derivatives, whenever I take those theta derivatives of a Legendre polynomial, I just get that. If I've got something that satisfies the Legendre equation, then that guarantees that that messy combination of theta derivatives will give us this. And I set all of this to 0. Now, this doesn't look like anything too easy, but just bear with me here. If I isolate one term, if I just focus on one piece of this, fix the value of L, I've got 1 over r squared. I'm going to take this r derivative times r squared partial squared VL by partial r squared plus 2r partial VL partial r minus L times L plus 1 VL over r squared, all of that equals 0, or partial squared VL partial r squared plus 2 over r partial VL partial r minus L times L plus 1 over r squared VL. What does that equation look like? That should look familiar from a couple of weeks ago. I mean, I've made it a little bit fancy with all these L's and subscripts and stuff. But remember the Euler equation, d squared y by dx squared plus, or there was, you could write it two different ways. You could write it that way, ax squared times d squared y plus dx squared plus bx dy dx plus cy equals 0. Or I could divide everything by x squared, and I get a times the second derivative plus b over x times the first derivative plus c times y over x squared equals 0. And what were the solutions to that equation?
Isn't it x to the n?
Yep.
In this case, r to the n.
So our solutions will have to be r to the n. So partial VL by partial r will be nr to the n minus 1, and then 2 over r partial VL by partial r will be nr to the n minus 2. And the second derivative will be n times n minus 1 times r to the n minus 2. And so when we put all this together, we've got n times n minus 1 r to the n minus 2 plus 2n r to the n minus 2 minus L times L plus 1 r to the n minus 2. And you're thinking, wait, isn't VL r to the n? Yeah, but I divide by r squared there. And all of that's 0. And I cancel the r to the n minus 2. And I'm left with n squared minus n plus 2n minus L times L plus 1 equals 0, or n squared plus n minus L times L plus 1 equals 0. So n will be -1 plus or minus the square root of 1 minus 4 times negative L times L plus 1 over 2. Or -1 plus or minus the square root of 1 plus 4L squared plus 4L over 2. Now the thing inside the square root is this whole thing is the square root of 2L plus 1 squared over 2. So we get -1 plus or minus 2L plus 1 all over 2. So we either get -1 plus 2L plus 1 over 2, or -1 minus 2L minus 1 all over 2. The first one is just L, because the -1 and the +1 cancel. The second one is -2 minus 2L all over 2. That's a 1, that's a 1, that goes away. So we get minus L plus 1. And strictly speaking, we should have some coefficients there. So when the dust settles, I could write V of R as the sum from L equals 0 to infinity, A sub L R to the L plus B sub L R to the minus L plus 1, whole thing times PL of cosine theta. Any questions? Anyone? Well, one question you could ask is, what are AL and BL? And the answer is that's going to depend on the details of your scenario. That's going to depend on your boundary conditions. That's going to depend on whether you just have a single point charge, or you have a dipole or a quadrupole or whatever. But whatever it might be, it's going to be a sum of things like this. And in an E&M class, you'd go into exactly when you approximate it as a monopole or a dipole or a sum of those or whatever. But mathematically, because we're writing it in spherical coordinates, and because it's symmetric about the axis, it has to be written like that. Any questions? Okay, well, one limitation of what I just did is that I was assuming rotational symmetry. But plenty of things are not rotationally symmetric. What if I've got this problem? Del squared psi equals 1 over c squared, partial squared psi, partial t squared. That's the wave equation. And due to the physics of the situation, due to what we know about the way that the waves are traveling, this thing is not symmetric. Our wave is going to depend on phi. So we could break it into terms of the following form: f of r PLM. Actually, I'll stick with PLM of theta e to the I m phi. That PLM I'm calling it PL because it's certainly related to the Legendre polynomials, but I'm putting an M in there because the phi dependence is more complicated. This should be PLM times e to the I m phi. And then here we've got our f of r out front, because everything shows up everywhere. It's just that it's a product of all these things everywhere. Actually, let's write it more simply. I'm just going to write everything in terms of psi for now. I'm not going to start breaking it up into pieces with elaborate names quite yet. All right, that's the wave equation. Now, we know that if sine theta is defined to be x, then I can write all of this in the form 1 over 1 minus, sorry, my bad. I can write this as 1 minus x squared times partial squared psi partial x squared minus 2x partial psi partial x plus L times L plus 1 psi. But then I've also got this over here, okay? Well, sine squared theta is 1 minus cosine squared theta, or 1 minus x squared. So that's nice. That's going to be an easy thing. And what did we say last time about the dependence on phi? It's got to be an eigenfunction of the second derivative, so it's got to be an exponential of some sort. And if we want it to be the same, whether I am working at an angle phi, or phi plus 2 pi, or phi plus 4 pi, or phi plus 6 pi, then psi has got to be proportional to e to the I m phi. And that second derivative is going to give us a minus m squared psi over 1 minus x squared. And all of that is 0. And that's called the associated Legendre equation. It sounds very formal. It sounds like some very boring thing, and it sounds even more boring than it is. It sounds like, you know, some sort of business development consortium. We are the Associated Legendre Property Development Group, okay? It sounds like the most boring bureaucratic thing imaginable, but that's its name, the Associated Legendre equation. And I could go through the algebra that leads us to the solutions to it, but it turns out that the solutions are very simple. They are often written as PLM of cosine theta equals e to the I m phi times the following. Sine squared theta to the, actually I'll write slightly, I'll simplify some things. Sine theta to the absolute value of m. And it's to the absolute value of m because whether I've got m equals 2 or m equals minus 2, I wind up squaring sine theta. And whether I've got m equals 1 or m equals minus 1, I just have sine theta. And then you take a derivative of order absolute value of m, which means if m equals 0, we don't take any derivatives. We've just got PL of cosine theta, and we're done. All right. If m equals 0, we've got e to the I times 0 times phi. E to the nothing is just 1. We get sine theta to the 0, and anything to the power 0 is 1. And if we don't take any derivatives, we've just got PL of cosine theta. So if we have the rotationally symmetric solution, m equals 0, it's the same thing as we had before. But if we have something different, then we just take derivatives of PL and we multiply by powers of sine theta. And there's a long proof that you can go through which will show that that's correct. But the reality is that this is one of those equations where 99% of your effort with it as a physicist is going to be using the solutions, not deriving the solutions. We write down so many things in physics in terms of what these functions that are called spherical harmonics. There are solutions to that equation. So I'm not really cheating you out of anything that you'll do as a physicist if I say that this is one of those things that just works. I know it sounds hideously unrigorous, but it's not like this is one of those solutions one of those equations that we spend time proving the existence of solutions to. There are equations where the very existence of solutions is a contested issue, or the existence of solutions of a particular form is a contested issue, or for certain parameter values, the solutions exist, and for certain parameter values, the solutions don't exist. Or for certain parameter values, the qualitative behavior of the solutions changes drastically. This is one of those things that we just use. It's a bit like in an experimental lab. Yes, you need to understand your electronics, but at some point, the fact that the light bulb turns on is not your major concern. There are other things that are your major concern, but you take it as a given that the LED can turn on, and what you focus on is, okay, if this LED turns on, it's an indicator of something else. This is one of those parts that we just almost never worry about. PLM of cosine theta, the associated Legendre function, has very weird properties and very weird normalization. And the normalization of that function is so weird that I think the textbook frankly does you a disservice by spending a whole bunch of time on how if you have negative m instead of plus m, then we multiply by or divide by a bunch of factorials of L plus m or L minus m, because that's not the form in which people use it. The textbook spends several pages on that. Here's the form in which people use these things. They use these things in the form YLM of theta phi equals -1 to the m times some constants times PLM of cosine theta times e to the I m phi. And here are the important points. The -1 to the m, that's historical. These are for the normalization. These guarantee that it satisfies the differential equation. Here are the key properties you need to know. 1, If we plug that into the wave equation, all right, if you plug it into the wave equation, you take the Laplacian on it, all of those angular derivatives give you back minus L times L plus 1 times the original function. Okay, that is the single most important thing. And you can verify that for some specific cases. It's worth doing, but the general proof is not really used. Now, maybe for people who are trying to generalize this to n dimensions to look at rotationally symmetric functions in n dimensions because they want to solve some higher order, some higher dimensional problems, maybe they need to care about those solution techniques. For the vast majority of projects where you're working in three-dimensional space, you don't. So again, key point, if the Laplacian acts on it, you get back a bunch of constants times your original function. 2, if I integrate over all angles, I get 1. If I take one of these functions and take its absolute value, square the absolute value, integrate it, I get 1. YL prime, M prime, theta, phi, whole thing, complex conjugate. So these form an orthonormal basis. All right, you can think of these as functions on the surface of a sphere because these are functions just of angular position. All right, so if I just wanted to look at a sphere, fix the distance from the origin and look at all the points at that distance from the origin, any function could be written in terms of those. They form an orthonormal basis. Proving the orthogonality for different m values is almost trivial because YLM is always proportional to e to the I m phi. So YL prime m prime would be proportional to e to the, and I should take the complex conjugate, so the product would be proportional to e to the I m minus m prime phi. And the integral of that product, what happens if I integrate a sinusoid over a full period? What do I get? I get nothing. I get zip, I get zilch, I get nada, I get 0. So the orthogonality for different m values is trivial. All right. The orthogonality for different theta values is a little more complicated to prove, but it would basically be the same procedure that we used above when I proved the orthogonality of the different regular Legendre polynomials instead of the associated Legendre functions. All right. It would be the same procedure. I've got this complicated differential operator. and I can act on a function with it, and I could use that to express one of the, I could say that since these are eigenfunctions of that operator, if I take all these derivatives, I get L times L plus 1 times the original function back. I could say that the original function is equal to 1 over that L, those L's, times those derivatives. So I'd have a function times some derivatives, and I'd integrate by parts. It's the same procedure. All I need you to take away from this is that the procedure we used before would work again. I'm waving my hands, but I'm waving my hands with a correct statement. A statement that can be derived using the exact same methods that we just used an hour ago. Oh, one other important thing. We're taking m derivatives. Okay, we're taking m derivatives here. Now, what's the order of PL? What's the order of the polynomial PL? Don't overthink it.
L.
L, yeah. So it has terms that go no higher than cosine theta to the L. So let's say that, I've got P3 of cosine theta. If I take the first derivative of it, I'm going to get a second order polynomial. If I take the second derivative, I'm going to get polynomial of order 3 minus 2 is 1. If I take the third derivative, I'm going to get a polynomial of order 3 minus 3 is 0. So I'm going to get a constant. What if I took the fourth derivative? What's the fourth derivative of a third order polynomial? What's the fourth derivative of x cubed?
0.
0. What if I had L equals 17? I could take 17 derivatives of that and get something non-zero. But as soon as I took that 18th derivative, for God only knows what reason, I would get 0, which means that m can only be between minus L and plus L. That's important. So if L equals 0, I've got one polynomial. I've got one spherical harmonic. If L equals 1, I've got 3 harmonics because I've got minus 1, 0, plus 1. L equals 2, I've got minus 2, minus 1, 0, plus 1, plus 2. L equals 3, etc. So in general, I've got 2L plus 1 harmonics. And any function of theta phi can be written as a sum from L equals 0 to infinity, and another sum m equals minus L to plus L of CLM times YLM of theta phi. And how do you think we would find those coefficients? How have we always found the coefficients when we expand something in terms of orthogonal functions?
Inner product.
Take an inner product. So CLM, or don't ask me why they make one of them a subscript and one of them a superscript. That's one of those things that just lingered. It's like irregular verbs. Every language has them. God only knows why. So that's how we do that. On Friday, we're going to practice some of that. I'm going to have you play around with these Legendre, with these spherical harmonics, look at some graphs of them in Mathematica, and expand some functions in terms of them. compute some inner products of different functions with them. And then next week, we're going to start talking about Bessel functions, which are yet another set of orthogonal functions that can be used to solve the wave equation in certain coordinate systems. Any questions? Then the last thing I will say is that we can get, honestly, Wikipedia has a perfectly good table of spherical harmonics. The textbook has a table of spherical harmonics. Wikipedia goes to pretty high order. As you study this table, just look at it and search for patterns. You will see that as you go out to larger m values, you get more factors of sine theta. So if you look at y20, you've just got a Legendre polynomial, 3 cosine squared theta minus 1. If you go out to y21, you've got sine theta and a first order polynomial of cosine theta. If you go to y22, you've got sine squared theta, and you've got a 0th order polynomial of cosine theta, which is to say you don't have a cosine theta. And at L equals 3, again, y30, you've got a cubic polynomial of cosine theta. You increase m, and you become quadratic in cosine theta, linear in sine theta. Increase m again, you become linear in cosine theta, quadratic in sine theta. You increase m again, you become cubic in sine theta, independent of cosine theta. That's a pattern that holds for all of these. If you really need to learn the theory of these, if you have a specialized project where the detailed properties matter, you can learn them, but for now, I want you to get comfortable using them. That's all. Have a good day.
Thank you, Dr. Small.
You're
We'll see you
welcome.
Friday.